Hello, I'm Lewis and this is DIY Machines, and in this project I'll show you how you can build your own smart chessboard for both local and online remote play. Though this board has a great single player mode, if you build two and bond them together digitally, you can then send one to a friend or loved one so that you can play chess together over the internet with real chess pieces and only a few seconds delay. It's a great way to share some time and to connect with people who are physically distant. This 3D printable chessboard has plenty of tricks up its sleeve, such as checking that you play by the rules and warning you when you don't. It can also suggest your next best move if you want. It also contains a formidable computer opponent to play against thanks to the internal Raspberry Pi. And I think it looks super cool when played in the evenings. Except for the electronics, it is entirely 3D printable. The LEDs beneath the playing surface communicate a lot of information about the game to you, whilst also creating a very cool effect by underlighting our chess pieces. The clear ones were printed on my Elegoo resin printer and look great. The others are printed on a traditional FDM printer. The Smart Chessboard is powered by USB. You can plug it into the mains when you're indoors, but can also enjoy many hours of untethered play outside or on your coffee table using a common USB battery pack. This project has been kindly sponsored by PCBWay, a great place to source your own PCBs. More about that later. As feature rich as the Smart Chessboard is, it's actually made from very few components. You'll need some filament for the 3D printed parts, as well as some LEDs. You'll need the sort where you get 30 per meter on the roll, a Raspberry Pi and micro SD card, OLED screen, an Arduino Nano, a logic level converter, 10 6mm push buttons, 2 wiring blocks, a USB dip board, and some bolts. As always, you'll find a list to all of these parts and where you can find them online down below this video and on this project's page at my website. We will need to start by printing the 4 main parts of the base assembly. I printed mine in a wooden fused PLA and added a brim to help with the bed adhesion. I put links to where you can find the 3D printable files in the description below. There is no need for support when printing these parts or any of the others for this project. Once printed, they are then simply glued together. Ensure that they are pressed together firmly whilst the glue sets. The last one is best added from underneath. Next, we will add the LEDs to the main surface of our chessboard. For this, you're going to need to cut 8 lengths of 8 LEDs from your roll. Cut straight through the centre of the solder pads. Don't worry if you find that one of your cuts has solder on the joint. You can still cut through this just like the others. Now, with our lengths of LEDs cut, you should add some solder to the 3 pads at both ends of each strip. This will make attaching wires to these much easier later. We will wire our LEDs in a zigzag pattern going back and forth across the surface of the chessboard. You'll need to pay close attention to the arrows on both pieces. I've put some arrows here on the 3D print which need to match up with the arrows that you'll find going along the strip of your LEDs. The arrows found on our strips of LEDs represents the direction that the data takes as it moves from one pixel through to the next. To the first strip in the bottom right corner, we'll add a set of 3 28cm long wires. They can be trimmed in length later. You can then slide the strip into position, being careful not to catch any of the LEDs. As we continue to zigzag up through the chessboard, we'll use 5cm long wires to join each of the returns. I found it easiest to prepare 21 of these wires before adding them to the board. Keep repeating this for the remainder of your strips, remembering to pay attention to the directional arrows on the printed board and your LEDs, and be careful with your solder joints. When you find yourself at the end of the last LED strip, attach a couple of 16cm long wires to only the 5V and ground connections. You can then go ahead and print the 4 sections of the playing surface and pop those into place temporarily. By the way, if you prefer to follow a wiring diagram as you go through the electronics, then you'll find a link to this one that I've prepared down below the video. But don't worry, I'll continue to step through the remainder of the electronics now. Next, we'll turn our attention to the main control panel. I printed mine in both grey and white filament and changed colour after just 5 layers. After you've 3D printed one of your own, we can glue into position 10 of the small tactile switches. You'll need to orientate the switches so that the legs run from side to side along the top and along the bottom like so. Take care when gluing the switches from behind that none of the glue finds its way to the front. Once dry, we can then set about to connect all of the ground connections of our 10 switches together in series, one after another. Start by connecting a 13cm long wire to this leg on the switch for A1. We'll then use several shorter lengths of wire to bunny hop between each of the switches, connecting their grounds together. Use a 5cm wire to go around this first return and an 8cm wire to go around the second return. To be able to connect each of our buttons to the Arduino, we'll need to add one more wire to each of them. Now, you can either label these as you go along or use the continuity feature of a multimeter to figure it out later. Solder an additional wire to each of the buttons following the suggested lengths shown here. Once these have all been attached, you can thread them through these hoops to help keep your work nice and tidy. Now we can take our Arduino Nano and begin to connect to it the work which we've done so far. If you decided to use a multimeter instead of labeling your wires earlier, you need to set it to its continuity mode and then connect one probe to the common ground and then the other probe to an unused button wire. You can then press each of the buttons in turn until you find the one which will be shown by a reading on your multimeter and more than likely a beeping noise. Okay, let's start connecting our buttons to the Arduino. The button A1 connects to pin D5, button B2 to pin D6, button C3 to D7, button D4 goes to Arduino's D8, button E5 to D9, F6 to D10, G7 to D11, H8 to D12, the wire coming from OK is connected to A1, and the wire coming from Hint is connected to D3. Then the button's common ground wire can be connected to any of the 3 ground connections on the Arduino. Next up is the backlighting for our control panel. For this, you should prepare and tin 3 strips of 2 LEDs. Solder a trio of 15cm long wires to the first LED strip, then 8cm LED strip, 4.5cm LED strip, and the final 14cm. After you have printed the LED's mount, we can then pass the first pair through and stick in place with its self-adhesive backing. Repeat this back and forth, ensuring the arrows on the print match the arrows on the LED strips. To connect these LEDs to our Arduino, the center digital wire heading into the first strip is to be connected to D4. We can also take the opportunity now to connect the data in wire going in at the bottom of our chessboard to our LEDs to pin A5 on the Arduino Nano. Whilst we have our soldering iron still hot, we can add some additional wires to the Arduino. Solder a 15cm long wire to each of the Arduino serial pins. These are marked as TX1 for transmit and RX0 for receive. Attach a 7cm long wire to both the 5V and one of the unused ground connections. We can now glue the LED assembly for our control panel onto the rear of the buttons. You'll find a notch in one and a protrusion in the other, which are there to help you align them. Just use some glue of your choice to seal them firmly together. To bring together all the 5V connections and all the ground connections, we can use our 2 wiring blocks. You'll need to connect both the 5V power lines coming from either ends of our chessboard LEDs, the 5V line from the Arduino Nano, and the 5V from the control panel LEDs to one of our blocks. And to the other block, connect both the negative ends of our chessboard LEDs, the Arduino Nano, and our control panel LEDs. Before we can fix this part in place, you should thread the 14cm wires coming from the end of our control panel LED run through this little tunnel at the end of our board. You can now fix the control panel in place using 4 of your M3x6 bolts. We now find ourselves at a great place to test both the buttons and the LEDs which we have installed so far. To do this, we'll upload a simple test script to the Arduino Nano temporarily and see what happens. Your computer's USB power supply and the Arduino Nano are not able to provide enough power to light all of these LEDs at their full brightness. So the code will limit their brightness for now, but don't worry, they will be much brighter later. Next up is adding the ability to power our chessboard from outside the board using a USB connection. You'll need to solder a 12cm wire to both the ground and power connection on your USB board. This can then be held in place by 2 M3x6 bolts. Now you can connect the positive and ground wire coming from our USB board to their respective terminal blocks along with the other wires. We can now connect an external USB power supply to our board using our new port, and you should find all the LEDs light up just as they did the first time around. To illuminate the coordinates around the edge of our chessboard, we can add a couple more strips of 8 LEDs. These strips are going to need to turn around a very tight corner on your board, so use a 2, 2.5 and a 3cm wire to join the two together. This will help later on when you put them in place. Once you've added these, you can join the first one to our wires coming through the tunnel next to our control panel. Pass the strips carefully through the tunnel in the first trench, go around the corner, and then pass the far strip through the other tunnel. You can then use some glue to help keep your LEDs roughly level and in line with the squares of the chessboard. Reconnecting the USB power supply to the outside of the board will allow you to check the LEDs again, and this time you should see that these ones that we've added around the outside of our board join in with the animation. Great work so far. Now, quickly before we continue, I want to take a moment to thank all the awesome people who've helped make both this project and all my other projects possible here on YouTube. First off are the patrons of DIY Machines. Their kind and generous support is used towards funding the electronics in designing and prototyping these projects. Thank you. Their support has proven very crucial over the last year, and I am and always will be grateful for it. I also want to thank everybody at 3D Jake for kindly providing the filament needed to bring this project to life. Now, before we start adding the brains in the form of the Raspberry Pi to our project, we need to upload the correct final code to our Arduino Nano. For the next stage, we will install the Raspberry Pi operating system onto our microSD card. Then we'll boot this on the Raspberry Pi so that we can install the Python scripts along with Max Chess, which will be there to referee your game, and Stockfish, which is the open source chess engine which you can play against locally. Now, as more people build more of these chessboards and play with them, it's incredibly likely that the code is going to evolve and improve over time. Because of this, I've written out these software steps over on my website. This way, future me can keep it up to date as the project improves. So head over there, follow the steps of setting up the software on your Raspberry Pi, and once you've done that, jump back here and we'll finish off the last of the wiring. All that remains now is to connect the last of our electronics together, and then we can start playing chess on our chessboard. You can now connect the wire coming from TX1 on our Arduino to the pin B1 and the wire RX0 to the pin B2. Add a new 7cm long wire between VB and our 5V power block and the ground pin and the ground power block. Attach some new 12cm long wires to VA, A1 and A2 on the shifter, and you'll also need to use just a small length of wire to join OE to VA, both on the same board in this case. If you want to learn a bit more about using the TXS01OAT logic level converter for your own projects, then I recently made a short mini video on it, which you can find up here or a link to in the description down below. Turning our attention to the OLED display, attach 4 12cm long wires to the 4 points labelled as SCL, SDA, VCC and ground. The only thing left to connect now is our Raspberry Pi. I'm going to be putting a DuPont style connector onto the ends of the wires and then using that to connect it to the Pi. This is very easy and cheap for you to make yourself, and I've made another video to show you just how easy that is. But if you don't want to, or if you have a Raspberry Pi which doesn't have any headers already pre-soldered to it, then you can solder your wires directly to the pins. Once you've finished adding all the female metal connectors to your wires, we'll start to insert them into the plastic housing. For this, you'll need one which measures 5x2 and a single one on its own. Now the order that we insert them does matter, so I'll step you through which wire wants to sit in which channel now. When looking from the back, the top left one should be the wire coming from VA on the logic converter. The next one down should be the SDA wire from our screen, followed by the SCL wire from the screen. Then we skip a pin and connect a new wire here to the block of ground wires. On the other side at the top, we'll use another new wire to connect to the 5V block, followed by the screen's VCC wire. We then skip the third hole, but then connect the wire coming from A2 on our logic level converter, and this is followed by the converter's A1 wire. The remaining ground wire for our screen is added to its own DuPont housing. Fit your Raspberry Pi inside of the chessboard using the 4 M2.5 bolts. Use 2 M3 bolts to hold your logic level converter in place. The screen is then arranged inside its 3D printed panel from behind and held in place with some glue. The larger DuPont connector is then fitted so that the wire going to the 5V power block is connected to the Pi's 5V in the top right corner. The lone ground wire for the screen is to be connected to the 7th pin down on the outside edge, just 2 below our larger connector. The panel itself can then be screwed onto the chessboard with the last of our M3 bolts. The last parts which we need to add to our chessboard are these 3D printed coordinate labels. These are simply printed and then glued into position. And there you go, that's your chessboard project complete. You can now print some pieces of your own. If you'd like to support the channel, you can find the pieces that I've used available for a small donation over on my website or in the description below. Don't forget to check out some of the other projects such as this hidden shelf edge clock, and if you've enjoyed it, please consider subscribing or sharing this project with someone who may like to build one of their own. Otherwise, until next time, ciao for now. One quick thing before I go. That's to say thank you to PCBWay for sponsoring this video. Personally, I'm currently learning to create my first PCBs, and they have been great to work with whilst I get to the grips of this. If you've wanted to have a go yourself at creating a PCB, or if you already know what you're doing, now there's a great time to try ordering some through PCBWay. Usually, they offer 10 PCBs for $5, but if you're a new member, they'll give you a $5 bonus, effectively getting your first PCBs for free. Try them out at PCBWay.com. You'll also find a list of the parts on my website. Oops. To power all of these LEDs at full brightness, so they will light up in a slightly lesser amount. No. And install the Python programs that I've covered.